Today we are going to learn about logic and proving mathematical statements as we dive into one of the most fundamental yet oddly satisfying topics in mathematics, parity. Yes, we are talking about the age-old battle between even and odd numbers, and the ironclad rules they follow when you add, subtract, or multiply them. You might be thinking, why should I care about parity? Parity is everywhere. It is in computer science, cryptography, number theory, and even everyday life. Ever played a board game where you needed to move an even number of spaces to land exactly on a square? Ever notice how some math tricks magically work without you actually doing much calculation? That is parity in action. So what exactly is parity? Parity is a mathematical property that classifies an integer as either even or odd. And here is the best part. Every single integer in existence belongs to exactly one of these two categories. With no exceptions, it is like a super strict VIP club with only two types of members. Let us start with the law-abiding citizens of this club, the even numbers. Even numbers are the neat, predictable folks of the number world. They always follow the golden rule. They can be divided perfectly by 2 without leaving a remainder. Think of them as the highly disciplined members of a mathematical society, always willing to split into 2 equal parts with no drama. If you take an even number and divide it into 2 groups, each group gets an equal share. No fractions, no leftovers, just a clean even split. Mathematically, we say a number is even if there exists some integer such that the number equals 2 times that integer. This simply means that an even number is always a multiple of 2, or divisible by 2. The usual suspects are 2, 4, 6, and so on. But do not forget the negatives, -2, -4, -6. Yes, they too obey the evenness rule. Whether positive or negative, an even number is always neatly divisible by 2. And then there is the special case 0, 0 is even. Some people hesitate when asked whether 0 is even, but rest assured it fits the definition perfectly. You can write 2 times 0 equals 0, and dividing 0 by 2 still results in a whole number 0 itself. So yes, 0 proudly belongs in the even number club. On the other hand, we have the rebels. The odd numbers are the misfits of the number world. They refuse to conform to the even number rule and simply will not be divided by 2 without causing trouble. When you try to split an odd number into 2 equal parts, one side will always end up with an extra piece. They are the rule breakers, the ones who refuse to be evenly shared, always leaving a remainder of 1 when divided by 2. Mathematically, we say a number is odd if there exists some integer, such that the number equals 2 times that integer, plus 1. It simply means that an odd number is not a multiple of 2. It also means an odd number is always 1 more than an even number, making it impossible to divide perfectly into 2 equal whole parts. The troublemakers are 1, 3, 5, and the list goes on. The negative rebels, like -1, -3, and -5, follow the same pattern. All of these numbers still refuse to be split evenly in half. No matter what, you will always be left with a remainder of 1, and that is it. Every integer, no matter how big, small, positive, or negative, fits into one and only one of these two categories. There are no half-even or half-odd numbers. If it is not even, it is odd, period. We say that two integers have the same parity if they are both even or both odd. In other words, they belong to the same team. On the other hand, we say that two integers have different parity if one is even and the other is odd. Now that we have unlocked the mystery of even and odd numbers, let us dive into the real fun. What happens when we add, subtract, or multiply these numbers? Are the results predictable? Can we figure out the parity of a sum or product without even doing the math? Spoiler alert, yes we can. But before we start waving our magic wands, let us take a step back and ask what mathematical operations we are actually dealing with here. Since parity is strictly reserved for integers, we need to be a little discerning about which operations keep us safely in integer territory, meaning which operations are closed for integers. Addition, subtraction, and multiplication are the trusty workhorses that always produce an integer when you start with two integers. They are definitely on the team. Division is the rule breaker of the group. Unlike addition or multiplication, division does not always play fair with integers. Sometimes it works out like 8 divided by 2 giving 4. But 10 divided by 4 gives 2.5, which is clearly not an integer. Since parity only applies to whole numbers, division is sitting this one out. Exponentiation is a bit of a roller coaster. When you raise an integer to a positive integer power, everything stays neat and predictable. But things get spicy when you introduce negative exponents, which result in fractions. And an exponent of 0 just makes parity irrelevant. So for our parity discussion, exponentiation is only invited if the exponent is a positive integer. Before we build our master table, let us talk about the counter number. That is the magical number that, when added to a given number, results in 0. In other words, if you have a number, its counter number is simply the negative version of that number. It is the ultimate undo button. Here's a cool rule about counter numbers. They always match the parity of their original number. If your starting number is even, its counter number is also even. If it is odd, the counter number is also odd. Your number may flip signs, but it never switches teams. Now let us roll up our sleeves and build a parity table together, filling it in as we speak. We will start with two key players. Let us call them the first number and the second number. Since each number can be either even or odd, we need exactly 4 rows to cover all the possible combinations. Let us start by filling in the addition column. What happens when we add our two numbers? The golden rule here is that if both numbers share the same parity, meaning both are even or both are odd, their sum is even. Let us write even in those two spots in our table. But if they have different parity, meaning one is even and the other is odd, their sum is odd. Let us write odd in those rows, and because math goes both ways, we have the vice versa rules. If you know that a sum is even, you can be absolutely certain that the two starting numbers had the exact same parity. Vice versa, if the sum is odd, you instantly know the two starting numbers had different parities. Next, let us fill in the subtraction column. The rule here is practically the same as addition. If the two numbers have the same parity, their difference is even. Let us write even in those rows. If they have different parity, their difference is odd. Let us write odd in those spots. And just like addition, the vice versa rules apply perfectly here. If you were looking at an even difference, you know for a fact that two numbers had the same parity. Vice versa, if the difference is odd, they had different parities. The addition column and the subtraction column match perfectly. No matter what parity your starting numbers have, adding them or subtracting them gives you the exact same result. Moving on to the multiplication column. The rule here is that a product is only odd if both of the starting numbers are odd. So for that bottom row where we have odd and odd, let us write odd in the multiplication column. For every other row, it takes just a single even number to infect the whole product and make it even. Let us fill in even for the rest of that column. The vice versa rule is incredibly powerful here. If you know a product is odd, you know for a fact that both starting numbers were odd. There is no other way to get an odd product. Vice versa, if you know a product is even, you can confidently say that at least one of the original numbers was even. Finally, let us complete our table with the power column, where we raise our first number to a positive power of the second number. The trick here is that the exponent does not change the parity at all. The result always matches the parity of your base number. So looking at our rows, if our first number is even, let us write even in the table. If our first number is odd, let us write odd in the table. We do not even need to look at the second number. The vice versa rule is just as straightforward. If the result of a power is even, you know the base number had to be even. Vice versa, if the result is odd, the base number had to be odd. Let us take a step behind the curtain. We filled out our table and we know the rules, but in mathematics we do not just accept things because they look like they work. We prove them. But before we dive into these satisfying proofs, if you are enjoying this mathematical journey, make sure to hit that subscribe button. It really helps the channel out and ensures you will not miss any of our upcoming math deep dives. Let us start by bringing back our two VIP definitions. An even number can always be written as 2 times some integer. For our proofs, let us call that integer k, so an even number is 2 times k. An odd number is an even number plus 1, so it can be written as 2 times some integer. Let us call it me plus 1. First up is the negative counter rule. The rule states that a number and its negative counter number always have the exact same parity. Let us prove it. If a number is even, it can be written as 2 times k. Its negative is negative 1 times 2 times k, which equals 2 times negative k. Since negative k is just another integer, the result is 2 times an integer, meaning it is still perfectly even. Now what if the number is odd? An odd number is 2 times k plus 1. Its negative is negative 2 times k minus. To make this fit our strict odd number definition, which needs to end in a plus 1, we use a little algebra trick. We rewrite negative 2 times k minus 1 as negative 2 times k minus 2 plus 1. Then we factor out a positive 2 from the first part. This leaves us with 2 times the group negative k minus 1, all with a plus 1 tacked on the end. Since the group inside the parentheses is just an integer, we have 2 times an integer plus 1. The parity stays exactly the same. Next, we have the same parity rule for addition. The rule states that if you add two numbers that have the same parity, whether they are both even or both odd, the result is always even. Let us prove both scenarios. First, adding two even numbers. Let us say we have our two even numbers, 2 times k and 2 times m. If we add them together, we get 2 times k plus 2 times m. We can factor out the 2, leaving us with 2 times the group k plus m. Since k and m are integers, adding them together just gives us another integer. So we have exactly 2 times an integer, making the result perfectly even. Now for the second scenario, adding two odd numbers, we take 2 times k plus 1 and add 2 times m plus 1. When we add them all up, we get 2 times k plus 2 times m plus 2. Notice how every single piece is now a multiple of 2. We factor out the 2 from everything, leaving us with 2 times the group k plus m plus 1. Since the whole thing is 2 times an integer, the two odd pieces have combined to make the result completely even. Then there is the different parity rule for addition. This rule states that if you add two numbers with different parities, meaning one is even and one is odd, the result is always odd. Let us prove it. We take our even number 2 times k and add our odd number 2 times m plus 1. This gives us 2 times k plus 2 times m plus 1. Just like before, we can factor out a 2 from the first part, giving us 2 times the group k plus m. But this time we have that plus 1 dangling at the very end. The whole thing looks like 2 times some integer plus 1. That perfectly matches the definition of an odd number. Moving on to the subtraction rule. The rule states that subtracting two numbers gives the exact same parity results as adding them. We can actually get this proof for free. Remember the negative counter rule we just proved? Subtracting a number is exactly the same as adding its negative counter number. Because the parity does not change when we flip the sign to a negative, all the addition rules for same parity and different parity apply perfectly to subtraction as well. Next is the rule for multiplying by an even number. The rule states that any integer multiplied by an even number results in an even number. Let us prove it. What happens when we multiply an even number 2 times k by literally any other integer? Let us call that random integer x. The product is 2 times k times x. Because all this is just multiplication, we can group the k and the x together, so we have 2 times the group k times x. Since there is a 2 sitting right at the front, the entire result is a multiple of 2. It does not matter if x was even or odd, that single even number infects the whole product and forces it to be even. Then we have the rule for multiplying two odd numbers. The rule states that the product of two odd numbers is always odd. Let us prove it. We take our two odd numbers, 2 times k plus 1 and 2 times m plus 1, and we multiply them together using the FOIL method. We end up with 4 times k times m plus 2 times k plus 2 times m plus 1. Look closely at those first three pieces, they're all multiples of 2. We can factor out a 2, giving us 2 times the group 2 times k times m plus k plus m, but we still have that plus 1 hanging on to the very end. The entire result is 2 times an integer plus 1. The product is definitively odd. Finally, the power. The rule states that an integer raised to a positive integer exponent retains the exact same parity as the base number. Let us prove it. We know that raising a base number to a positive exponent just means multiplying that base by itself over and over again. If the base is even, we are just multiplying even times even times even. We just proved that an even number times anything is even, so the result will always stay even. If the base is odd, we are multiplying odd times odd times odd. We just proved that an odd number times an odd number stays odd, so no matter how many times you multiply it by itself, an even number can never sneak its way in as the result stays odd forever. Now, you might be wondering, what about proving those vice versa rules from scratch? We could rely on process of elimination, but for practice, let us prove the vice versa addition rule for an even sum as a standalone rule. If the sum is even, the numbers must have the same parity. We will use a brilliant tool called proof by contradiction. In a proof by contradiction, we assume the opposite of what we want to prove is true, and then show how that leads to a totally impossible mathematical situation. Imagine for a moment that they do not have the same parity. That would mean one is even 2 times k and one is odd, 2 times m plus 1. We already proved that adding an even and odd gives us 2 times the group k plus m plus 1, which is definitively an odd number, but wait. We started with the absolute fact that the sum is even. Saying an even sum is equal to an odd number is a total contradiction, because assuming they have different parities leads to an impossible situation. Our assumption must be wrong. They absolutely must have the same parity. What about the vice versa addition rule for an odd sum? If the sum is odd, the numbers must have different parities. Let us imagine they actually had the same parity. If they were both even, our earlier proof showed their sum would be even. If they were both odd, our earlier proof showed their sum would also be even. In both of those scenarios, we get an even sum, which directly contradicts our starting fact that the sum is odd. Therefore, it is impossible for them to have the same parity. They must be different now for the vice versa multiplication rule. If a product is odd, both starting numbers must be odd. Let us imagine the opposite. Suppose at least one of the numbers was even, say 2 times k. If we multiply 2 times k by our other number, let us call it x, we get 2 times k times x. Since there is a 2 out front, the product would be an even number, but we already established the product is odd. This impossible contradiction means neither number can be even. They must both be odd. Finally, let us prove the vice versa multiplication rule for an even product. If a product is even, at least one starting number must be even. Imagine the opposite. Suppose neither was even, meaning both were odd. We just proved that an odd number times an odd number always gives an odd product. But our product is even. This contradiction proves that they cannot both be odd. At least one of them has to be even. Now it is time for you to put these actual proofs into practice. Let us do a quick mental workout. Suppose you are looking at the equation x plus y equals 27. Can both x and y be even numbers? Think about our addition rules. 27 is an odd number, and we know that an odd sum only comes from adding two numbers with different parities. So no, they cannot both be even. One must be even and the other must be odd. What if someone asks you to multiply 41 by 73 by 89? Wants to know if the answer is even or odd. You do not need a calculator, you are looking at three odd numbers. Odd times odd is odd, and multiplying that result by another odd keeps it odd. The final product is definitively odd. Finally, what if someone claims they found two mysterious integers where their sum is even but their difference is odd? You can confidently tell them that is impossible because we just proved that the sum and difference of any two numbers must always share the exact same parity. And there you have it, folks. No magic, no guessing, just solid mathematical logic proving exactly why the rules of parity work every single time.